If you've ever had a window seat during heavy turbulence, you've seen something that looks terrifying. The wing outside your window isn't staying rigid. It's moving, bending, flexing up and down in a way that seems like it shouldn't be possible for a piece of metal. The wingtip might move 2 or 3 meters from its resting position. The entire structure is flexing like a diving board, and your brain immediately tells you something is wrong. Wings shouldn't bend. Wings should be stiff and solid. Bending means breaking. Your brain is wrong. Those wings are bending because they were designed to bend, and that flexibility is exactly what keeps them from breaking. This is the counterintuitive engineering behind aircraft wing design. Flexibility isn't a weakness, it's a feature. To understand why wings need to flex, you need to understand what forces they experience during flight. A wing's primary job is to generate lift. That lift force acts upward, distributed along the entire span of the wing. At cruise, the total lift generated by both wings equals the aircraft's weight. For a Boeing 787 at cruising weight, that's roughly 250,000 kilograms of lift being generated. Each wing is producing about 125,000 kilograms of upward force, but that force isn't concentrated at one point. It's distributed along the wing, with more lift generated toward the root near the fuselage and less toward the tip. Now here's the critical part. The wing itself has weight. The structure, the fuel inside the wing tanks, the engines hanging beneath the wing, all of this mass is being pulled downward by gravity while the air is pushing the wing upward. This creates bending stress. The wing is being bent upward by lift, while simultaneously being pulled downward at various points by its own weight. In normal flight, these forces are in balance. The wing bends slightly upward and stays there. You might notice from the window that the wing curves upward a bit compared to how it looks on the ground. That's normal loaded deflection. But turbulence changes everything. Turbulence is essentially rapid changes in the air's vertical velocity. When the aircraft enters a turbulent region, the wing suddenly encounters air that's moving upward or downward faster than expected. If the wing hits an updraft, the effective angle of attack increases instantly. Lift spikes upward. The wing experiences more bending force than in smooth air. If the wing hits a downdraft, the opposite happens. Angle of attack decreases, lift drops, and the wing experiences less upward force. These changes happen fast. In severe turbulence, the wing might experience rapid cycling between increased and decreased lift forces, multiple times per second. Now imagine if the wing were perfectly rigid. A rigid wing would transmit all of these rapid force changes directly into the fuselage. Every spike in lift would jolt the airframe. Every drop would shake the structure. Passengers would experience violent acceleration changes, but worse than comfort, a rigid structure has no way to absorb energy. When forces spike, a rigid beam experiences peak stresses at specific points, usually near the attachment to the fuselage. Those peak stresses can exceed material limits. This is how rigid things break. They can't flex, so they fracture instead. Flexible wings solve both problems. When a gust hits and lift increases, the flexible wing bends upward. That bending absorbs energy. The force transmission to the fuselage is softened. Peak stresses are reduced. When the wing rebounds from the gust, it bends back down. The structure oscillates rather than taking sharp impacts. This is the same principle as the suspension in your car. The springs and dampers absorb road bumps so that the chassis doesn't have to take the full impact. Flexible wings are essentially aerodynamic suspension, but here's where the engineering gets really clever. The wing isn't just passively flexible like a rubber band. It's designed with specific stiffness characteristics to achieve particular behaviors. Wing designers tune the structure so that as the wing bends upward, the angle of attack at the tip actually decreases slightly. This happens through a phenomenon called geometric twist under load. When the wing bends up, the outer sections naturally twist leading edge down relative to the inner sections. This twist reduces the lift being generated at the tips precisely when lift is spiking. It's a self-stabilizing system. The more the wing bends, the less additional lift it generates, which limits how much it continues to bend. The wing naturally moderates its own loads. This isn't accidental. It's deliberately engineered through careful placement of structural elements. The position and orientation of spars, ribs, and skin panels all contribute to this behavior. Let me give you some real numbers to illustrate wing flexibility. The Boeing 787 is famous for its flexible wings. During certification testing, Boeing bent the wings upward by approximately 7.6 meters, about 25 feet, beyond their normal position. The wings held. They didn't crack, didn't break, didn't show any signs of structural failure. That test was conducted at 150% of the maximum expected load. It's called an ultimate load test, and every commercial aircraft must pass it before certification. Why test to 150%? Because regulations require a safety margin. The wing must handle the worst conditions that could realistically occur, with extra capacity beyond that for unexpected events. In normal operation, including severe turbulence, the wing will never approach those test loads. The 3-meter deflections you might see during a rough flight are well within the normal operating envelope. Think of it this way. The wing you're watching bend 3 meters was proven to handle 7 meters of bend without breaking. You're seeing maybe 40% of its capability. The material science behind modern wing flexibility is fascinating. Older aircraft, built primarily from aluminum alloys, could flex to some degree, but aluminum has a limited fatigue life. Every bend cycle damages the material slightly. Over thousands of flights, this fatigue accumulates. Aluminum wings had to be designed with compromise, flexible enough to absorb loads, but stiff enough to limit the number of flex cycles. The Boeing 787 changed this equation by using carbon fiber reinforced polymer for its wings. Carbon fiber composites have excellent fatigue resistance. They can flex repeatedly without accumulating damage the way aluminum does. This allowed designers to make the 787's wings more flexible than any previous commercial aircraft. More flexibility means better load absorption, which means lighter structure needed for the same safety margin. It's a virtuous cycle. Better materials enable more flexibility, which enables lighter weight, which improves fuel efficiency. The Airbus A350 uses similar composite construction and achieves similar flexibility. Both aircraft have noticeably more wing bend than older aluminum designs. There's another aspect of wing flexibility that matters: flutter prevention. Flutter is a dangerous phenomenon where aerodynamic forces interact with structural flexibility to create runaway oscillations. If the wing's natural frequency matches certain aerodynamic conditions, energy can feed into the oscillation rather than damping it. The wing bends more, which creates more force, which causes more bending. If flutter occurs and isn't stopped, it can destroy the wing in seconds. Aircraft are designed to have flutter speeds well above their maximum operating speeds. Part of this design involves ensuring that wing flexibility characteristics don't create problematic resonances. Wing stiffness isn't uniform. Different parts of the wing have different flexibility in different directions. This is deliberate. By tuning the structural dynamics, designers ensure that flutter modes are suppressed. You might have seen videos of aircraft undergoing ground testing where the wings are artificially vibrated. These ground vibration tests map the wing's natural frequencies and mode shapes. The data ensures that no flutter conditions exist within the operating envelope. There's one more flexibility feature worth understanding: winglets and their attachment. Modern winglets, those upturned tips you see on most commercial aircraft, generate significant aerodynamic loads. The forces on a winglet try to bend it outboard and twist it relative to the wing. The connection between winglet and wing must be flexible enough to avoid stress concentrations, but stiff enough to maintain the winglet's aerodynamic orientation. Some modern wing designs integrate the winglet smoothly into a curved wingtip rather than having a sharp junction. The Boeing 787's raked wingtips are an example. This curved design distributes loads more smoothly than a traditional abrupt winglet attachment. So what should you actually feel during turbulence? When you see the wing bending significantly, what you should feel in the cabin is relatively mild compared to what would happen with a rigid wing. The flex is absorbing energy that would otherwise reach you. If the wing were rigid, those same turbulence encounters would produce sharper, more violent cabin motions. you'd feel more. The structure would absorb less. The fact that you can watch the wing bend dramatically while feeling moderate bumps is the system working correctly. Your discomfort in turbulence is mostly psychological, driven by seeing the unusual wing motion and hearing unusual sounds. Structurally, the aircraft is handling conditions well within its design envelope. Commercial aviation has recorded instances of severe turbulence that bent wings significantly. In virtually every case, post-flight inspection revealed no structural damage. The wings did exactly what they were designed to do: flex, absorb, and recover. So the next time you're in turbulence and you see that wing bending in ways that seem impossible, remember what you're actually watching. You're watching engineering working perfectly. A structure designed to flex so it doesn't break. A material chosen for its fatigue resistance. A shape tuned for self-stabilizing loads. A system tested to 150% of anything you'll ever experience. That bending wing isn't failing, it's succeeding. Every flex is energy absorbed, stress distributed, and margin preserved. Wings bend because bending is how they survive. There's actually another aspect of wing design that passengers find counterintuitive. Fuel is stored in the wings, not in a central tank. And that placement is deliberate, directly related to the bending loads we've discussed. I've explained why in another video.